So if you could remember in the last lecture, we had started signal multiplexing, and we saw that one can multiplex signals by the help of amplitude modulation. And how is that possible? It is possible if I modulate signals of two users onto two different frequencies by using amplitude modulation. If I am using double sideband amplitude modulation, I will make sure that those two carriers, which are for each different user, have a gap of 2W or more than 2W, so that their spectrums do not clash with one another. Because one carrier will have a spectrum of minus W and plus W around its FC. The other will also have its lower and sideband, lower and upper sideband around its new FC. The difference between these two old and new FC should be 2W, so that the upper sideband for one user and the lower sideband of the other user do not clash or do not interfere with one another. And hence, the various message signals will be occupied in these separate frequency bands, and both the signals could be sent to a communication channel. This combination of separate message signals into a composite signal that is called multiplexing. So we will be covering frequency division multiplexing here. Now, division multiplexing, as shown in figure 3.31, you have k different users or k different message signals. Each message signal is passed through a low pass filter. This will make sure that now the bandwidth is up to W. If it is a low pass signal, so bandwidth will be W, minus W on the negative side and plus W on the positive side. Now, each restricted message signal will pass through a modulator. Now, all of these will be different modulators which will be working at different frequencies, making sure that their frequencies have at least a gap of 2W between the next frequency of the other modulator, or with respect to the adjacent modulator's frequency. So all of these are now amplitude modulated at different frequencies. They are all added, and then they are sent through a broadband channel which can pass all of these. So when they are received at the receiver, they will first of all go through the band pass filter. Now the band pass filter will be with respect to the modulator of each user. So output will be only the signal of, let us say, M1T around its designated frequency. So this will be a high pass signal, but it will be band limited, containing only the high pass modulated signal of M1T, so M2T and so on and so forth up till MKT. Now we will demodulate. We will demodulate with the same frequency with which we had sent, as we have studied in demodulator, and then we will pass through this product signal through a low pass filter to reject the high pass frequency or high frequency components, and you will just get the low pass component. Ending. So you can also see here, each signal first of all modulates separate case. Yes. If anyone has any question, you can ask. And then at the receivers, we have these band pass filters. The only desired signal comes out, then it is eliminated by a demodulator, and so on and so forth. Now, this is a very important implementation, especially in telephone exchanges. each voice signal is roughly of a bandwidth of 4 kilohertz at the baseband level. So we use single sideband. So even if it is modulated, we know we are just using single sideband, so it will still occupy 4 kilohertz, not 8 kilohertz like in double sideband. So first of all, 12 signals of, let us say, 12 different telephone users. Uh, each having 4 kilohertz. Telephone users or even radio users, mobile and radio users, if they are just using voice. So they will have a 4 kilohertz separation. So 12 into 4 kilohertz, each user having 4 kilohertz, you will get a 48 kilohertz group channel, which can simultaneously transmit 12 voice band signals or 12 different user signals. Then this group channel is again grouped or stacked together in frequency to form a supergroup channel, which will have typically 5 to 6. So if, let us say if there's 6, so it will have 6 into 48 kilohertz of bandwidth, roughly around 300, more than 300. Then this is transmitted over the channel, and let us say that you have a very large channel, and let us say you are sending the signal from one country to another, then a lot of signals from all of the country, they need to be stacked together. So you can have higher order multiplexing by combining several supergroup channels. So this type of hierarchy is especially employed in telephone communication systems. Next, very important is quadrature carrier multiplexing, and it relies on two carriers, cos and sine. We know cos and sine are orthogonal. All right. If you take the product and integrate over the time period, you know you will get a 0 for a cos and sine product. So they can also be separated at the receiver. So that this concept is used. So I have one signal M of 180 of one user, it is sent through a cosine. Another user signal is sent through a sine, same frequency, occupying the same bandwidth. They are added together, transmitted over the channel like this. And hence two users are being sent in 2W bandwidth. So effectively, they are still occupying W bandwidth or a single sideband spectrum, not a double sideband spectrum. They are actually double sideband signals, but as you can send two users in these double sideband signals, so you are effectively using a bandwidth of a single sideband AM. So you can see here, so you have M1 of t, M2 of t, one is goes with a cos, other goes with a sine. They are added, sent through a channel. Here you use a PLL to get the phase and to form the carrier of the exact phase as of the received signal, so that there is no phase shift. Multiply with the modulator, and if you will multiply with cos, here you will multiply with sine. Once you multiply with cos, you will get the cos part. Once you multiply with sine, you will get the sine part. And this we have also seen when we are studying, single sideband demodulation. So here you can also see that what is happening. So let us say your signal is multiplied by cos 2 pi fct. This signal which was sent through a cosine, and this was equal to AC M1t cos 2 pi fct. All right. So once it is multiplied, then you can very well see you can write the product as cos square, but this u of t, which is actually this signal, which contains cos and sine. So you multiply with cos, you will have a cos square here. Here you will have a sine times a cos. you will have cos square here and sine, and we know cos square is 1 plus cos 4 over 2, and cos 4, this will be rejected by the low pass filter, so you will just get the low pass signal. Here you have cos and sine, so you can use the um, sine formula. This sine alpha plus beta, which is cos alpha cos sine beta, or you can say sine alpha cos beta, whatever. So this can be written again as sum and difference of sines. So sum will give you, difference will give you 0, and that will be 0, sine of 0. So again, this will also be rejected by the low pass filter, hence you will just get AC over 2 M1T. Same thing you can do with the other part of the signal. Instead of multiplying with cos, we will multiply with sine. So you will be getting a sine square, which you can know is written as 1 minus cos 2 theta over 2, and hence you can get back the low pass signal, while the other will be rejected. So actually this is what is used in wireless industry. The previous one is mostly used for telephone, but in wireless, as we communicate through wireless channels, this quadrature multiplexing, quadrature carrier multiplexing is used. Heidi, if you have any questions, you can ask now. All right. Now another important industrial application of amplitude modulation is, AM radios or AM radio broadcasting. Now, what happens that you have this bandwidth of 535 to 1605 kilohertz that has been allocated to commercial AM radio, and now the carriers, remember the carriers will be in this will lie in this range, so they cannot be at 535 or up till 539, because each voice message has a bandwidth of 5 kilohertz, and once it is in the passband channel like this, so it will occupy a bandwidth of 10 kilohertz. So it should be at 540, so that 5 kilohertz below up till 535 and 5 kilohertz above up till 545. Then it will properly lie in this range. If you use a carrier, let us say 537 or 538, then part of its sideband will lie below 535, and hence it will violate the industrial allocation to that radio channel. So radio channels we have seen, they apply AM for transmission. Bandwidth is 5 kilohertz for the low pass or the band or the baseband signal, and we know that we have billions of receivers and we have few transmitters, so double sideband is justified. With that conventional where 1 plus a mt, where we make sure that mt is normalized, and again we multiply with m so that it is always less than 1, and it becomes a good conventional amplitude modulation signal, amplitude modulated signal. So that will obtain the major objective, which is the reduction in the cost of the implementation of the receiver by use of a simple envelope detector. Now, as we have to take care of also the high frequency part here, so this is the receiver of our AM radio or AM receiver, is as it is called as very famous super heterodyne receiver, and it is not only used here. Variations of these heterodyne receivers, they are used in also other applications of communications, from radar and navigation. There you also find heterodyne receivers, and many times if you go in industry, you will be working that we are making a heterodyne type of receiver. So you will see what is a heterodyne receiver. Here you have not only the radio frequency, this is the carrier. You have a mixer, local oscillator, which was all in the previous sections, but you also have this thing which is called the intermediate frequency amplifier. This is an addition of heterodyne receiver. Previously you could have this and this, but then you directly had an envelope detector. But now you also have an IF or intermediate frequency amplifier. So we all know we have a tuner. It is a variable capacitor which tunes uh, the RF amplifier and the frequency of the local oscillator to the desired radio station. This can also be done digitally, as you can see in, nowadays you can have this digital tuning. Now what is actually happening here? Why this is a super heterodyne receiver? Because every EM signal is first of all converted to a common IF, a common intermediate frequency of 455 kilohertz. So we do such type of conversion at the receiver so that if we are receiving any AM signal, it could be of any frequency. As we have just seen, it is going roughly from 550 to 1600. Alright, 540 to 1600, roughly 550 to 1600 kilohertz. But they were the actual frequency carriers. So once they are received by a radio, it converts them to an intermediate frequency, which is 455 kilo. So from 1600 or 1200 or 550, the carrier frequency is transformed to this IF frequency, and we will see how it is done. Now the advantage is that for every radio station you will just require a single IF, because after this all the frequencies are at 455 kilohertz. So you will just need an amplifier that is working around 455 kilohertz. Right. And the amplifier is also designed to have a bandwidth of 10 kilohertz. So what is the advantage? So if you have tuned to some radio station, that radio station will be converted to 455 kilohertz. That will be amplified, and the amplification will be just around the bandwidth of 10 kilohertz. The amplification will be for a bandwidth of 10 kilohertz around 455. This means that all other frequencies which are actually coming out from the mixer with their frequencies shifted to different uh, frequencies, the IF amplifier will just pass the IF frequency 455 kilohertz, and it will reject all the other frequencies that are not around IF. Okay. And we will see only that frequency will be at IF for which you have tuned your RF amplifier and local oscillator. Now, how this is done, how we bring the signal to an intermediate frequency IF. This is done by having your oscillator, local oscillator, set to a frequency FC plus FIF. So if your radio station has a frequency of FC, you will select your oscillator to have a frequency of FC plus FIF. So in this way you will tune into the FC frequency, as well as that FC frequency will be converted to FIF. So this means the tuning range of oscillator will be, FC is going from roughly from 450 to 1600, or you can say the exact value was 540 to 1600. So your LO will go from 540 to 1600 plus 455. So 1600 plus 412, it comes out to 2055, and you can see 445 plus 455, it comes out to be 995. So your local oscillator will be going from 995 to 2055 kilohertz. So you will use the mixer that will multiply or mix. We have seen what happens, mix, and then you pass uh, through the appropriate band pass filter. So you will mix or you will multiply with this carrier, and the result will be that you will get two cosines. One will be at IF, the other will be at 2C plus IF. But this 2C will be rejected by the IF amplifier. It will only pass the frequency around FIF. So he has not done the mathematics. I will just show you. So this was my signal, this is your AM signal. Assuming this one of this MT has been, normalized, multiplied by A, or you can just assume that the magnitude of MT is always less than 1. Right? This was the signal. Now it is multiplied. We are not multiplying here with cosine 2 pi FCT as in, our previous discussions. As in our previous discussions of demodulation of a double sideband signal. We are multiplying it with a cos which has this frequency of FC plus FIF. So it is 2 pi FC plus 2 pi FIF. So if I multiply again, product of cosines, is equal to sum of cosines plus difference of cosines, and cos minus is cos minus theta is cos theta. While this is frequency, this cosine stands at 2FC, so it will be definitely rejected by the IF amplifier, which is only passing the frequencies around IF of only 10 kilohertz. This is very high. This will be definitely rejected, and you will just get your signal, high frequency signal, at now converted from FC to FIF, okay, and containing your conventional signal. Now this signal will pass through an amplitude envelope detector, as we have seen, for conventional demodulation of conventional AM, you had to pass this through an envelope detector. So we will again pass it through an envelope detector, and hence by passing, we have seen previously, you will just get your M1 of T. So we have seen that it rejects all other signals except around FIF, which is actually a signal of FC. So your FC will pass. But there is another problem, and that is the problem of image frequency. The IF amplifier cannot reject an image frequency. So image frequency has to be rejected by the RF amplifier. And this is done as follows. The RF amplifier is before the IF amplifier. So RF amplifier will reject the image frequency, while IF amplifier will reject all the frequencies which are adjacent or around the desired FC frequency, and that FC frequency has been converted to IF, and all the other frequencies around it will be rejected, and hence you will just get your own radio station signal. So what is this image frequency and how it is rejected? So it's rejected by making sure that the bandwidth of your this VRF means radio frequency, or you can say the bandwidth of your RF amplifier, this one, this RF amplifier, this bandwidth is always kept less than 2 IF. All right, it has to be greater than 10 kilohertz, or you can say it has to be greater than 5 kilohertz if the bandwidth is with respect to the baseband signal. So the bandwidth of the RF amplifier is always less than 2 IF. All right, so it is greater than BC. So here we take BC to be 10 kilohertz because we are talking about pass band, or high pass. When the signal has been modulated to higher frequency, this BC will be 10, double the frequency. So it is greater than 10 kilohertz, but it has to be less than 2 IF. If it is less than 2 IF, then the image frequency will be rejected. So BC is the bandwidth of AM, which is now at this point taken at 10 kilohertz. So then we can reject the image signal. Remember, what is the image frequency? Image frequency is FLO plus FIF. FLO was actually equal to So image frequency is FLO plus FIF. Now you can see here in my notes that alright, FC dash, this is image frequency, is equal to always FLO plus FIF. But what is FLO? We know FLO local oscillator was actually FC plus FIF. This means the image frequency is FC plus 2IF. Now question is, why do we call this image frequency? We call this image frequency because it is passed. It is an image of, it looks as if it is an image of FC, and it is also passed by the IF amplifier. Now here you have seen that if the frequency is at FC, it is passed by the IF amplifier. Now here you will see that even if the frequency is FC plus 2IF, it will be also passed by the IF amplifier. So it is 1 plus M2T cos 2 pi FC dash, which is FC plus 2IF from here, multiplied with the same signal, oscillator plus LO frequency, and this multiplication is again written as sum and difference of cosines. So you can see this will be equal to FC dash is equal to FC plus 2IF. So hence you will get here 4 pi FC, and this 4 plus this will become to 6 pi FIFT. But this will be definitely rejected by the IF amplifier because this is standing at 4 FC, or you can see 2 FC frequency, 2 pi into 2 FC, 2 FC frequency, and the IF only passes around FC or around FIF. Rest of them are rejected. So this is a very large frequency, will be definitely rejected, which just passes around FC. Now in the difference you have this thing, this cancels. I've just substituted the value of FC dash, which is FC cancels. We have 4 pi FIF. Now 4 pi means 2IF, and this 2IF will again subtract from it. So you will again get a simple simple FIF. So this signal which is of an other radio station which was being sent at the image frequency is also being passed by the IF amplifier, okay, and it looks as if this is from the same radio station, but it is actually from a different radio station. So after this, it will just go to the envelope detector, and the envelope detector will be having two signals, one plus M1T and one plus M2T. Now, how to get rid of this, M2T or this M2T which is at the image frequency? We make use of the RF amplifier. We know that this FC dash is equal to FC plus 2 FIF, or 2 times the intermediate frequency. But you can see that this frequency will always be less than the carrier plus 2IF divided by 2. So this will always be greater, because this frequency is just 2IF divided by 2. This is half of this factor. Alright. So you can very well see this frequency will always be less than this frequency. But this frequency, you can very well see, okay, will be less than this frequency. FC is same, but you can see that what is 2IF? We know bandwidth of an RF amplifier is less than 2IF. Alright. So this means that this total factor will be less than this total factor of value. And you can see this is the upper limit of your RF amplifier, and this frequency lies above this upper limit, hence this frequency will be rejected by the RF amplifier. Same thing has been explained in the book, and you can also read it from here. And you can see the figures here. So this is your FIF, the intermediate frequency at 455 kilohertz, or BC bandwidth, 10 kilohertz bandwidth. Then this is your FC signal, your original FC, which is actually FLO minus IF. FLO is equal to FC plus FIF. FIF cancels, and this is FC. So FC can also be written as FLO minus IF, because FLO is equal to FC plus FIF. So around FC frequency, you have also a bandwidth of BRF, the bandwidth of the RF amplifier, which is around FC, but is less than FIF. So the image frequency is formed as FLO plus FIF, which is a very large, which is actually FLO, which is FC plus IF. This is FC plus 2IF. So, and this is at the maximum, this will be just about FIF. So hence this frequency will be rejected by the amplifier of radio frequencies. Then you have envelope detector, it power goes through a loudspeaker, and you have automatic volume control. So you can adjust if you want more volume, you can adjust the amplifier so that you get louder sound, louder signal strength. So this finishes our 3 chapter, and we would have finished it in 3 lectures, because because of Ramzan. So it came out to be up till this lecture also, almost more than you can see we have taken almost more than half of this lecture also. So now we go to the next chapter, and that is angle modulation. Now, previously we were studying amplitude modulation. Amplitude modulation, we know they are non-linear, but industrially you can call them linear modulation methods, because strictly speaking, I think loosely speaking, you are, yes, you is a non-linear system, but you are not changing the spectrum. You are just shifting the spectrum from, one frequency to another frequency. So we can say with respect to, spectrum shape, it is linear, but we know it is non-linear in a strict sense, because you are changing the frequency. Once you change the frequency, the system becomes non-linear. But what happens for angle modulation? Angle modulation is uh, completely non-linear. It also changes the spectrum. It does not shift the spectrum as for AM. It actually changes the spectrum drastically. There are two methods. One is called FM, the other is called PM. And uh, in FM systems, the frequency of the carrier is changed by the message signal, while in PM system, the phase of the carrier is changed by the message signal, and they are non-linear, definitely. They are called angle modulation methods. So it is more complex to implement. It is difficult to analyze, and we can only do its approximate analysis. One property is that we will be seeing it will be expanding its bandwidth. There you could see it was just translating in AM, you were just translating the frequency from baseband to passband. So it might become double or half. It was just simple translation. Here you will see that we are changing the spectrum and we are expanding. We have a bandwidth expansion of the signal. Bandwidth is becomes many times as compared to the bandwidth of the message signal. Actually, it tends towards infinity. But industrially, we can come to a, uh, a bandwidth, the restricted bandwidth, not an infinite bandwidth. So question is that if you have greater complexity, implementation complexity, then you have high bandwidth occupancy. Why we are using these systems? These systems are used when you want to have a high degree of fidelity, or you want a very high degree of quality. You don't want any noise, because you will see that these systems are very much immune to noise. They have a very high degree of noise immunity. They are not affected by noise. So if you want to have very high quality of noise, quality of your signals, you can use FM systems. There they will be occupying larger bandwidth, but you will have a clear hearing of your signals. That is why they are used for high fidelity music broadcasting. Even if you want to, let us say, listen to, or the radio station people, they decide that this is a very important speech, they might transfer that speech to FM, because in that case you will have a very good immunity against noise. So they have a constant envelope because their amplitudes are not changed. That is an advantage. Now let's go to the mathematics of angle modulated or FM and PM signals. So angle modulated signal can be written as follows. You could see here. Here there's a change here in the phase. So FC is the carrier and phi t is the phase, the instantaneous phase of your signal. Now we know the phase is always given as follows. The total phase. The total phase will be 2 pi fct phi t, and then the instantaneous frequency will be actually fc plus derivative of phase with respect to t That will give me, you know, derivative of this will be something 2 pi into the f5 frequency, divide by 2 pi, you will get the frequency corresponding to this phi t. This is like this. So instantaneous frequency is the frequency of the carrier plus the derivative of the phase divided by 2 pi. So you will get the instantaneous frequency from here. So if MT is the message signal, I will have a short break of 1 minute. Please don't go away. Sorry for the break. So you can see this is the instantaneous frequency. The phase will be given as follows. If we are using a PM system, then this phi t vary linearly with the signal. All right. So this is the signal, and you will just multiply with some constant, and you will get the instantaneous phase for PM signals. Now what happens for FM? The instantaneous frequency varies with the signal. So instantaneous frequency is this. It is the total instantaneous frequency minus the carrier frequency. Uh, the frequency deviation varies with the signal. So frequency deviation is the instantaneous frequency minus FC, and this varies with the message signal. So this deviation varies with the message signal, where Kp and Kf, they are just phase and frequency constants. So we can summarize that our phi of t could be equal to Kpmt for PM systems. But for FM systems, you can see that KFMT is equal to this, and hence phi t will be equal to 2 pi KFMT and then integration. So this derivative cancels. So pi t will come out to be 2 pi KF integral MT. I will again have a break, sorry. चेक करने से समझा मैंने फिर भी निकाल दिया मुझसे।
तो जो नीचे है इधर भी है और नीचे भी है।
अच्छा, bismillah, coming back. So you can see that phi of t could be kpmt for pm, while phi of t will be integral of mt for fm. Now this relation gives us a very important relationship between PM and FM systems. And what is this relationship? The relationship will be if, for example, I have my empty signal, but I first integrate my empty signal and then I fed to a PM system. So it will become a FM system. So we can say that phase modulation of the carrier with the integral of the message signal, that gives me an FM signal. All right, you are doing phase modulation, but you have integrated the signal before. And integration into a constant is actually FM. Vice versa, you can see that if I take the derivative of the signal beforehand and then I pass through my FM system, the derivative integral, it will cancel, and in effect it will become. I first take the derivative and then I pass through a FM. So derivative will cancel with integral, and in effect your derivative FM will come out to be a PM system. Both those systems are very much related, and hence we can go through these two systems simultaneously. So you can see here that an FM system can be written as integrator of the signal plus a PM, and a PM signal can be written as differentiator plus FM. So this has also been shown in this figure also. So this was your M of T signal. And you can see its FM comes out to be as follows. This is one signal, constant amplitude will give one frequency, constant amplitude will give another frequency, FM signal. For PM, this will give one phase, this will give another phase. And this is the integral of the signal. So its FM, this will be increasing in frequencies. Its frequencies will be increasing. That is why it will be grouped together like this here. Higher frequencies for higher amplitudes. So this is the signal looks as follows. Now if I pass this integral of the signal to my PM, so it will look as if it is as follows. And as you can see that if you pass the integral of the signal to a PM system, so in effect it becomes as if you are doing its FM modulation. That is why these two are equivalent.
वो चेक कर रहे हैं।
So demodulation of FM signal involves finding the instantaneous frequency, while in demodulation of PM signal, we find the phase of the signal. Once we find the phase, we can get empty. Once we get the uh, deviation, instantaneous frequency, then subtracting the carrier, you get the deviation, then you can get back the empty signal. So the maximum deviations for phase will be given as follows. So we have maximum value of the signal times kp. This will give me the maximum deviation, because phase modulation was kp into mt. So maximum will be maximum of mt into kp. This will give the maximum phase deviation. And then the maximum frequency. Here you could see that the in frequency deviation, the difference of the deviation is proportional to the message signal. So the maximum deviation in frequency, will be equal to kf times maximum m of t. Kf time maximum m of t. So let us do one example. So we have m of t given as follows. Now we want to do its FM or PM. First I do PM. So I just take the signal, multiply with the KP. This is my PM signal. Then I do its FM. In FM, I have 2 pi kf integral of mt. Integral of course will be sine over 2 pi f, and 2 pi cancels. So you just get 2 mf 2 pi f 2 pi cancels f of m. So it will be kf a over fm. So we have calculated their phi's. Just substitute their phi's inside their expression. Expression was a cos 2 pi fct plus phi t. Phi t is equal to this for pm, and phi t is equal to this for fm. So kpa is another constant. Similarly, beta f is another constant. So you can write this in terms of constant as follows. And these constants are called modulation indices of PM and FM systems. And you can also write this uh, beta P and beta F in terms of other non-sinusoidal signals, where we have a baseband signal which has some bandwidth. In that case, BP remains the same, Kp into maximum of MT, and this will come out to be, again the numerator is same, Kf into maximum of MT, which was A. Here it will be whatever the signal, it's maximum. But FM, that was the frequency of the sinusoid. That will be replaced by W, where W is the bandwidth of the message signal. All right, is replaced by W. So maximum phase deviation is beta P. Maximum frequency deviation divided by the bandwidth gives us beta F. Now another thing is of narrow band angle modulation. It is that type of angle modulation in which phi of t is much less than 1. The values are such that phi of t is not a large number, rather it is very much less than 1. With this approximation, our signal, our actual signal was cos 2 pi fct plus phi t. So I can open that some cos alpha plus beta as cos alpha cos beta minus sin alpha sin beta. As phi t is very much small, cos phi t becomes 1 and sin phi t is equal to phi of t. This signal comes out to be like this. Now you can see that this signal is very much like my AM signal. Why? In AM signal you have the message signal multiplied with a carrier, but there our carrier was cosine. Here the carrier is minus sign. That's the only difference. Okay, and you can see this is the pure carrier and this is the double sideband signal. So its bandwidth will be also the bandwidth for narrow band. The bandwidth will be the bandwidth of AM signal because it is the AM signal. This approximation, the phasor diagram is also shown here. You can also see here that for amplitude modulation, the whole signal was the carrier plus this 1 plus AMT, the conventional. So the whole signal was lying on the cosine. But in this narrow band angle modulated signal, carrier is along the cosine, but this message signal is along minus sign. And we know that sine and cosine, they are orthogonal, or they have phase shift of 90 with respect to one another. So we can see that conventional AM and narrow band. So narrow band angle has far less amplitude variations, because you can see it is phi t into cos or sine, but phi t into sine or cos will not vary much because phi t is a small number. So, but narrow band does not provide better noise immunity as compared to conventional AM, which we'll be seeing in chapter 6. So it is seldom used, but they provide a good intermediary stage for the generation of actual wideband angle modulated signals that we will be studying in future. I'm sorry for the interruptions that came. If you have anything that you want to ask, please ask. With respect to the previous lecture, or this the part that we have covered. All right. So spectral characteristics. So we have seen that they are nonlinear and their characterization is not simple. So we take simple signals, do their FM or PM, and then analyze their spectrums to get a result for complicated signals, to get a generalized result for complicated signals. So we will first of all study the spectral characteristics of an angle modulated signal when the modulating signal is just a cosine or a sine, sinusoidal or a cosinusoidal signal. So we assume that the message signal is a sinusoid. So sinusoid in PM it will be just sinusoid into Kp. That will become your PM signal, but in your FM, your phi t, will be integral of your sine, so that will become a cosine into kf, 2 pi kf, and all that you have just seen. So the signal will be cosine 2 pi f ct beta. This beta could be beta f or beta p, and this could be sine or cosine. It is sine for PM, but it will be cosine for FM. So we are doing spectrum analysis of both the schemes, PM and FM, at the same time, because as we saw earlier that they are much related. So all right, time is up. If still you have any question, you can ask. All right, no one has any question.
Assalamu alaikum, sir.
Walaikum salam. Haan ji. Kaun keh raha ji? Who is speaking this?
फैजान सर, सेक्शन सी।
अच्छा
सर
अच्छा
सर वो ना एग्जाम्पल जो आपने करवाई है इस 4 चैप्टर में पहले ही, सर उसमें जो पहला स्टेप है वो जरा रिवाइज कर दीजिएगा।
अच्छा अच्छा। चलें, शुक्र है किसी ने सवाल तो पूछा। मैं देखा कि बच्चे पूछते ही नहीं सवाल। और इट इज 4.1.1 एग्जाम्पल, दिस एग्जाम्पल यू आर
जी
टॉकिंग
सर,
अबाउट।
सर जो फर्स्ट एग्जाम्पल इसमें एक ही आपने करवाई है वही वाली सर।
जी, तो यही एग्जाम्पल है। इसमें आपको फर्स्ट स्टेप इज वेरी इजी, फाइव टी ऑफ पी एम इज इक्वल टू ऑलवेज के पी इंटू एम टी। तो के पी इंटू एम टी। ऑलराइट।
ठीक हो गया सर। ये अपना एफ एम में सर ये जो हमने
हाँ
इंटीग्रेशन
एफ एम।
ऑफ एम
हाँ
इंटू
वेरी,
टाउ किया उसको कैसे यूज।
नहीं देखे ना अब, वो जाहिर है कि आप इसको टी पे लेके आना चाह रहे हैं, तो यू हैव टू इंटीग्रेट ओवर अनदर वेरिएबल टाउ। इंटीग्रल will be from minus infinity to t, and you're integrating the whole signal from infinity up till t time so that you get the phase up at t time. It's just simple integration. So you integrate your this signal with respect to tau derivative, tau independent variable. So cos will become a sine, and you know this will become a over 2 pi. A remains above 2 pi. Fm will come in the denominator. 2 pi cancels, and you have kf a over fm.
ओके सर, ये एफ एम सर
Okay, and
किस
you
चीज
put
से
the
है।
limits of sine. This is not fm, this is a phase of fm is this thing. It is
ओके
integral
ठीक है
of
सर,
the message,
ठीक हो गया
integral
सर,
of the
समझ आ
message.
गई। थैंक यू सर।
So, so I'm happy someone has at last asked the question. So I will take your attendance.